until too late at least. But I needed probably to do as best as I can today to don't have an extra delay tomorrow. So let me just remind you a few things. I mean, I started my first, let's say, class that I said it was part 0. Essentially, it was to discuss computer simulations. So I introduced you to the difference between what to make a model, how to solve a model. I introduced you this basic stuff to discuss a little bit computational physics, structural bioinformatics, these kind of things. Then on Tuesday, so the second class that I called part 1, it's where, in fact, I started dealing with electrostatic interactions. And I also make a few comments a little bit more about models, especially the continuum model. My last slide was this one, I was trying to show you some advantages when you were dealing with the continuum description of the solvent instead of a explicit model. You can probably have this picture in mind that the greatest advantages is, of course, the reduction in terms of points that you have to calculate for your interactions. So this is good, but even more important, another thing that we discussed was the difficulty that we have to get a proper dielectric response of the system when you do atomistic simulations. So very often you have this feeling that you are putting lots of details and you're going to get something better, but it can sometimes not be the case. Of course, I also introduced you some new or recent developed models where people were able to improve this description of the dielectric constant. They are able to reproduce experimental data in a much better way, which also opens new opportunity for people that would like to do atomistic simulations. So the point is, I would like to keep you aware that there are models for different things, and each model is good for a few or one or few things, and others are good for others. Eventually, they have problems in one side or another. This was, let's say, the main point. And also, during this previous talk, I introduced you to some landmark models in the history. And now, what I'm going to do is to really go to the first model that I think can be very good for us to have as a kind of base of the electrostatic interactions. It's the so-called TK or Tanford-Kirkwood model. So Kirkwood appears again, and this model is a very, very crude description of the system. But even so, it's surprising to see how such is very elementary and very simplistic model is able to capture the main mechanisms of physics. You heard in several talks this spherical Call approximation. I mean, that one thing that we often do in physics is to really identify the key elements of a problem or of a system and to be able to quantify this using our physical knowledge. And very often we invoke lots of approximations that eventually people say that, well, at the end, what do you have? There is even some phrase that with 2 parameters you can make even an elephant to walk and talk. But anyway, this is really a very crude description. I'm going to show you some comparison of experiments, and you can see by your eyes how good it can be, this model. But this model is also interesting for other reasons. It's the basis for most of the theoretical developers that have been developed later. So often, in order to test any new methodology, people try to reproduce things using this very simple model. And there are many other implementations that they were also developed on the top of this model. So this is central in several electrostatic interactions applications. So that's why I'm spending some time, and I'm going to follow the historical development. So I went really back in time. This model is from 1957. The fundamental basic mathematical equations, they came from 37, so it has more, just the model, I mean, it has about 60 years. The idea is that you take your protein structure. Here in one, you just imagine this as a protein, and you're going to describe your protein as a spheric object where your solvent is outside. You forget about any irregularity that you have in the surface, so you treat everything as just a single sphere, and inside you can put the position of specific titratable groups. Often, this is taken from crystallography data. If you have some binding ions, you can also include them, and everything should be inside this surface area, this spherical area. Outside here, we have the electrolyte solution. But you can see that there is a difference between 2 and 3. What is this difference? Well, we have to assume that we have contra ions and we can add salt to the system. So we can say that when they are coming closer to the interface, they are not going to be able to cross because they should have a size. So in this area here, 3, we treat these ions as point charges. But inside here, this layer between 2 and 3, you define a size. That's not going to appear explicitly, but it's going to be implicit. You're going to take into account this effect. So that's why you have a difference. And you can see that I can use a low dielectric constant or different dielectric constants to describe this interior of the protein. And then another dielectric constant, the solvent constant, to describe the outside part of the system. Well, although it's a very simple and sometimes elementary, yes?
Is it possible to apply this model for example, synthetic polyelectrolytes which have a high charge density?
Yes. Well, depending on what you like to calculate. I mean, in principle, you can model, if you like to use. In principle, you can model any macromolecule like this, but we have to see what's going to be the purpose of your calculation. Like, this kind of model is especially good if you'd like to describe or to map the surface of your protein, electrostatic fields, to have, like, to calculate free energies of interactions, these kind of things. But the idea can be used in different ways. Okay? There are people that, for instance, have used this kind of models to study adsorption of polyelectrolyte on the surface of proteins. Okay? Okay, so, but when they introduced this kind of a very simplified model, they also created a few problems to us. We don't know a priori what value I should use for the low interior, the low dielectric constants. People say, of course, that probably the dielectric constant for a medium that's not moving that much should be a small number. But we are mixing up macro and micro things. So at some point, this concept might break down. Another thing, we don't know exactly where we should put the boundary of this dielectric constant. In this picture, I'm putting the boundary exactly with this radius here, B. But in principle, it does not need it to be exactly the surface of the protein. Because if you are thinking about mobility, maybe it can be a little bit shifted, it can be a little bit outside. So when they have introduced these things, they have introduced a big problem as well, because this has been under debate in the literature during the last maybe 30 or 40 years. What dielectric constant should we use to describe the interior of a protein? And I'm going to show you a few results. I'm also going to show my opinion in this business and some arguments to support my opinion. But anyway, this is the basis of the Tanford-Kirkwood model. You can see the original paper that I mentioned, and the ideas, as I said, the mathematical ideas, they came from a previous work from Kirkwood, and also the ideas that I introduced to you in the last class, where I was talking about this Lindström-Lange model. So these are the papers where you have all the details about this model. Just to simplify me, I'm not going to go into all the details. By the way, this kind of electrolyte treatments and things that I'm going to talk about also later, electrolyte solutions, you have a very nice analytical class where he went to the statistical mechanics basis of these things that Roth has provided us in the previous school. So just go to ICTP homepage and you can see the lecture from the previous school. I'm leaving this as a homework to you. What I'm going to use here is just the main ideas that you can extract from this statistical mechanics part. So either from combine his class with the papers that I just showed you, or going drilling yourself to the details, you are going to end up in this kind of equation. So when I get the Tanford-Kirkwood model, essentially I can write the free energy as a dependence of the charge and electrostatic potential in different points of the space, and I need to find one way to calculate such things. So any point outside the surface or inside the surface should respect an energy like this, a free energy like this. And what Tanford and Kirkwood had proposed that you can write this free energy as 3 terms, essentially. One that depends on the Coulomb interaction, so it's charge-charge interaction. Another one that depends on the solvent, and another one that depends on the salt. And then, of course, for each of these A, B's, and C's, you have a function for such things. And you, of course, you have pair interactions between all the explicit titratable and charge groups that you have in your model. These charge groups are the ones that you can, for instance, see here. So this is really a very crude and short approximation. When you were calculating the solvent and salt dependency, you're going to see more exotic equations that I'm not showing you right now. But for instance, in Natalia's talk, if I'm not wrong, she mentioned the Born solvation energy. The Born solvation energy is going to appear here when you have, in the solvent part, when you assume that you have just the first order or the first term of this, the expansion that's going to come out here. So there are functions here, and when you just cut this equation and you use the first term, you're going to end up in the Born solvation energy. This also helps me to illustrate how this model has been appearing in different parts of the electrostatics models that we have available. Okay? I'm writing down here this equation. So if you're not really that much into equations, don't be afraid. You can see here the term that depends on the solvent. And this is the one that if I make this n equal to 1, I'm going to get rid of part of these things, and I end up in the Born solvation energy. I'm also illustrated here a model that was derived based on the Tanford-Kirkwood on colloidal signs. So this is a model that I have used before to simulate micellar systems. And in exactly the same idea, the only difference that here we place all the charges at the surface and not inside. They are objects that they can move around this outlayer of the spherical objects, like you have in any kind of micelle. Okay? But it's exactly the same ideas. You can use the same equations. You have a low dielectric medium. You have to define the radius of this dielectric medium. You have to define how big you have for your particles, how big you're going to describe this area here where you have the solvent, and so on. Okay? If you have any questions, please just let me know.
Sorry.
Yes?
I didn't understand the basic model.
Yeah, this one. Oh, sorry.
Okay. So you have like a core in which we have like charges in specific positions, right?
Yes. Positions in this case that you can take from crystallographer data, for instance.
Okay.
You remove amino acids that are not titrable, so that we don't care about their positions because they're not going to enter in the equations, and we keep the coordinates of the atoms, the amino acids that can titrate. Okay. And eventually, like heteroatoms that can also be present, can have a charge. So everything that can have a charge, you put in a model. Okay. Another thing that might be interesting to make a comment here is like when they were doing this model, they assume full titration or full protonation. You don't have partial charges. You just go there and assume, okay, this is an arginine, so this arginine has +1. So the pH, although we are talking about electrostatics, pH does not enter in the picture yet. You can do a kind of, let's say, preliminary calculation to define the charge as a function of the pH, as maybe you can also use the analytical equations that I showed before, okay? But explicitly, the model is just like you just go in a position and specify, in this position I have this charge, and that's it. What else? The results. So let me compare things with experimental data. Typically, in order to test if a system, an experimental system, has electrostatic interaction as a driving force, what is done? I think I already mentioned in one of our group discussions. Well, the easiest thing to do is to increase the salt concentration. So if you increase the salt concentration, you screen out the interactions, and if this is the driving force, you should see a reduction in the attraction or the repulsion, depending in which regime you are. So very often what people do, they try to calculate free energies. For instance, here is if I have, for instance, a protein, 2 calcium ions, and they are going to bind in a specific position. So I can write down this process as this chemical equation where we can write down the free energy for different compositions, and what we are after is just this number. But if I know how to do this in a given condition, so let me use here the board. For instance, I have here my protein plus my ligand, and they form a complex. For this, I have a free energy associated with this process. Let me call this delta G1. Then, if I change, either I can make a mutation. So, for instance, I can have another protein, let me call here P prime, then I'm going to have another complex. And this, of course, is going to give me another free energy. Or I can do a change in my environmental conditions. I can change, for instance, the salt concentration. And this is also going to give me another free energy. One thing that's often interesting for us to do is to calculate the variation of this guy. Oops, sorry. So often we assume a condition that we know, and would you like to test if the change that I have done has improved or not this change, the complexation. So if this number here is positive, what does that mean? It means that this guy is increasing, and would you like the opposite situation? Because as much as this guy is increasing, it means that the change that I have done in the process has affected in a bad way, in a negative way, the complexation, for instance. On the other hand, all the time that I have a negative number here, it means that I'm going on the right direction to make the process more favorable. But often, instead of just work with delta G's, we work with delta pKa's. And if you remember, they go in the same direction. So they are equivalent. I showed you these things in the previous class. So delta pK here is essentially this delta G divided by a few constants, by one constant, actually. Okay? And as a function of salt concentration, that for some historical reasons, people like to work with the square root of this number. So here I have salt concentration. So I'm increasing salt concentration, and I'm measuring the free energy, the change in the free energy when I have a reference state. Typically in these experiments, people do the experiments using very low salt. So they have typically 1 millimolar, 2 millimolar. In this work, you can see that the reference state was 2 millimolar. So that's the first point here, 2 millimolar. When I'm increasing salt, what I'm observing? Well, I'm observing that it starts to increase delta pKa. So if delta pKa is increasing, this guy is increasing. If this guy is increasing, I'm going in a direction that I'm have a reduction in the affinity. So this is typical what you expect if it's a process driven by electrostatics. You increase the salt and you see that your binding is affected and it has been you have a reduction there. Well, in this plot, I have several data at the same time. I have experiments. So you can see that the symbols here, they represent experimental points. The solid line, they refer to Monte Carlo simulations, where the same model has been solved using Monte Carlo simulation. So it's the same model, the Tanford-Kirkwood model, but now instead of using analytical approach, I'm solving exactly the same model, but using Monte Carlo simulation. And the dashed line here is the Tanford-Kirkwood approximation. It's not that bad. I mean, you can see that with some calculations that you can do in your pocket calculator, you are able to estimate and to predict, especially at this low salt regime, very well the behavior of the system. And this is really quick. On the other hand, of course, as much as we increase the salt, we start to see deviations, which is expected. I mean, come on, look at all the approximations that we have done. Okay? In this case, the calculation here, the experimental data also was done for calbindin. Calbindin has, in this condition here, a net charge of -8. So we have a protein with -8, and I'm interacting with 2 calciums that have +2. Of course, just knowing this information, you already can see that this should be related to Coulomb interactions. So we can also test, remember, making mutations. So if I do a mutation, well, if I take an amino acid that is negative charge, and I mutate and make it at 1 neutral, I'm going to reduce the charge. So suppose that I do like here. I take glue and make a neutral version of this glue. I have now -7. And if I also take the aspartic acid and make a mutation, I have -6. So I know that it should reduce the affinity if the system is, of course, controlled by electrostatic interaction. And in fact, it is. I mean, you can see that already at 2 millimolar, we already have a pKa, a delta pKa here around 2.5. So this is the experimental proof that electrostatic is driven by electrostatic interactions. And moreover, it's a way to demonstrate how good or how bad, depending on the way that you prefer to see. I prefer to see how good is the Tanford-Kirkwood model, especially for low salt concentrations. And if I decrease the charge, I can see that the agreement starts to be even better. So from this result, we could already see that there might be a limit that I can go with this approach in terms of charge of the protein, in terms of salt concentration for binding studies. Yes?
In the PK model, the simulation is deterministic or stochastic?
This simulation is exactly using the same model and solving this model by a Monte Carlo simulation. Yes, so
The dot model are in there?
in the Tanford-Kirkwood model, you have analytical solution, so that's the analytical part. But I can solve the same model using Monte Carlo simulation. Remember the slide that I showed in previous class? For a given physical system, we make a model, and I have two choices. Either I solve analytically, eventually making extra approximations, or I do Monte Carlo simulation, or MED simulation. In this case, we have done a Monte Carlo calculation. Okay? Okay. So just to try to see how is the limit of these things, we start exploring two things. One was the net charge. So we made up a few models that were even more simple than this one. Instead of having the charge that can be anywhere, we put all the charge at the center. So I have a big central charge here that I call Z, capital Z. This charge here, Z, is going to be, if I have add up all the contributions from these tetrabral groups. So now I can vary Z as much as I want. So this is like a toy model. I can play different Z's here, and I can measure again the delta pKa's. So doing that, we could see that, well, for systems where the charge is smaller than 12, 13, eventually 14, we are still good to do the Tanford-Kirkwood analytical equation. We start to have problems for highly charged objects. I mean, when you go to proteins that are with more charge. So this is a way now to understand how far we can go or how charged can be my system. What is the take-home message here? If I'm working, for instance, close to the isoelectric point, where my net charge is closer to 0, for sure, I can use the Tanford-Kirkwood model because it's going to work. We are going to have charge around here where there is a good agreement. When I start departure from the isoelectric point, I can still do something. But if I go far away, probably my model is going to give an overestimation of the process. So that's another thing that I have to be careful with Tanford-Kirkwood models in general. They are going to break it down at some point. Another interesting result that we can see in this plot that probably you have noticed that there are two curves that I call it Tanford and two that I call Monte Carlo. They are on top of each other. Now what's the difference? We have been exploring what's the effect of the low dielectric constants. So depending on what measurement you're doing, this can be important. But if you are calculating deltas, like we have here, the effect of these dielectric constants or the dielectric interface is going to disappear. And we have used a vacuum for the low dielectric part to put it under very extreme conditions. This is the condition where we're going to maximize the effect of the low dielectric interface. And doing so, we can see that for deltas, essentially we see that they are on the top of each other. So there is no effect. So this was one result that was quite polemic at the time because people have this, depending on which background they have. If they're coming from colloidal science, they never were worried about the electric constant. To use a uniform number was okay. But people that were coming from the biochemical side, they were never comfortable with the idea that a unique dielectric constant number could describe a protein. Because you know that the mobility of a protein is different than the solvent. So the dielectric constant should be different. So there are, I mean, all these discussions that have been around. And here it was for the first time that we could see that, well, depending on what we are doing, it does not matter. We tested a little bit more things. I'm going to jump this slide, but in general, just to make a comment on this, make another simplified model, we can see that depending where you put your boundary, you can, in this case, I may change the size of this dielectric interface because we don't know where we should put. I have assumed that I could have exactly on the top of my protein surface. But in principle, I don't have this information. There are two parameters and I don't know the answer. What people typically do, they try to fit these numbers to reproduce some given experimental data. But if I just try to vary it then and get the estimation, I can see that depending where I put my boundary and where is the binding site, I can get even unphysical results. Here's an example. Depending on how I change the dielectric radius, we can end up into delta pKa is equal to 20, which is totally unphysical for systems like this. It's too big. Well, you can ask me things. Okay, you were comparing Monte Carlo with the Tanford-Kirkwood model, which is a kind of linear version of the Poisson-Boltzmann equation. What about if instead of using the Tanford-Kirkwood model, you make the same comparison with the Poisson-Boltzmann equation? We have done a comparison and the same picture holds. It's exactly the same thing in terms of dielectric constants. But if you compare the three cases, we can see that if you change the linear response by the nonlinear response, you improve the results. So now you can see that the middle plot here, the middle curve, starts to come closer to the Monte Carlo data. It's not a perfect agreement yet, but they are approaching each other. So that's a good point. I mean, I know that the part of the limitations that we can have in the Tanford-Kirkwood model is due to the linearization. And if I get rid of the linearization, at least I come closer to the experimental data, or in this case, the comparison between Monte Carlo and the analytical approach, or mean field approach. Okay, I was saying that this is polemic in the literature, so I should let you know about how the others think. There are examples that people were discussing. For example, they were trying to use atomistic simulations where they could try to estimate how could it be the dielectric constant, how is the change between the things. Because in the Tanford-Kirkwood model, we assume that either one number or another is like a phase transition. But in real life, you can see that it's a smooth transition. The problem is how we model something like this with just two states. So at some point, I have to define, okay, up to here is one dielectric constant, and up to there is another one. But we have to define this, and this is very much sensitive. Because if I have a dielectric interface, all the time that I calculate the potential, electrostatic potential, we know that as much as I move my charge close to the boundary, the potential can explode. It can be either negative, highly negative, or highly positive. And very close, a small difference in the separation distance here, you can have a huge change in the potential. So essentially, we can manipulate the numbers, just change a very small number your separation distance. So that's why it becomes a little bit tricky to use this as a fitting parameter. So this was one of the criticisms that I was making to other people. This is another paper that they try to use NMR to use arguments that you should have a dielectric constant that varies along the simulation, along the separation distance. Yes? I think the battery has gone. Rolf, do you need it? Okay, yeah. Yes. So maybe I should try to stay just in the middle here where the camera is. Let's see. Well, anyway, so this is one example of experimental paper together with theoretical data where they are trying to make a proposal that as a function of the separation distance of the center of the protein, you should have a different value. Essentially, what they are doing is to say that your dielectric constant should be a function of the separation distance. That's what they are trying to argue in these papers. Well, you have another one. Thank you. Obrigado. Não tinha percebido também. Thanks, Rolf. So, just to give you a little bit more feelings about this polemical subject, I'm bringing a few things. This is from Nathan Baker that works a lot with Poisson-Boltzmann. He has the software APBS. That's one example of software that you can use. And you can see the typical values that people have a tendency to use. So you can see that like vacuum is one, of course. Usually when you try to describe atomic polarizability, we go for numbers between 2 to 4. If depending on what kind of rearrangement you have, you say that you have 4 to 10. Depending if it's a little bit more long range, you can go to the higher numbers, these kind of things. In practice, I think we all agree that the values are more used for fitting reasons. So everything that I don't know and is not present there, I can just adjust my numbers in such a way that I can get a better agreement with the experimental data. So this is one problem. And in fact, I can show you, well, here we are comparing numbers that we can get for pKa's for different chemical groups that we have in this protein. This data, I forgot what yes, here we took the data for lysozyme, if I'm not wrong, from this Bashford and Karplus paper, where they have introduced a software called MID. It's one another Poisson-Boltzmann solver based on the linear version at least. And we decided to vary the dielectric constant of the protein. And you can see that you can easily produce any number that you want. But after some number, you start to have more or less a constant behavior. So it starts to be a little bit difficult to argue that to use 20 is different than use 40, then use 60 if the difference here is really small. You can see here that we are comparing the maximum deviation, the average deviation, and the RMSDs. So it's not really that significant. I mean, of course I can have any number, but if what's recommended is something around 4 to 20, well, if I say that I have something between 10 to 20, of course I'm going to end up in more or less the same numbers. My results are not going to be that much affected. But if I can manipulate a little bit, eventually this is going to help me to give a better result. Okay, so that's the point. I mean, if you are working under conditions that you can work with this 10, 20, 30, you are going to end up in the same results. Unless you can tune your model for a specific reason that you should work with an even lower dielectric value. So this is just one argument to complete the story, okay? That's the comparison in terms of dielectric constants. I have now just to go quickly, I don't know how much it's going to be important, this part for you now, because you probably have seen a few things already described by Eduardo, and I was thinking if I should remove or not. But anyway, let me go quicker to this part and try to show things from a little bit different perspective. I would like to remind you that we have typically in physics two different properties. I mean, we can have what we call particle properties, and we can have field properties. So typically, we can talk about forces here and about fields here, or potentials, and here, potential energy. So you can see all the mathematical relations between them, the representation in terms of vectors or in terms of scalars, and we can go from one to another. Depending on what you are doing, it's convenient to work in one or it's convenient to work in another. But, I mean, it's just a matter of how we prefer to make our, let's say, to use our equations. Okay? I think this is just to remind you that these properties that exist and how are the relations. So, to get the Poisson-Boltzmann equation, we can go back to the very basic physics, and I can take here the Gauss law, where you have this divergence of the electric potential. And you can see that this is related to the distribution of charge, and if I have a medium, the dielectric constant of the medium and the vacuum dielectric constants. So this is the basis that we have in electrostatics when you are doing your undergraduate studies. Okay? So I can also do a little bit of a tricky. I can just use the definitions that they were in the previous slides, relating the properties of potentials and vectors, which was there. So if I replace here this electric field by this function here of the potential, we can replace the Gauss law and get this divergent here with the power 2. And this is going to give us the so-called Poisson equation. Of course, I have done in a very simple way. I've not described too much. I didn't make any comment about the Maxwell law that this can also be. But this is giving an idea, I mean, what's the source of the things, and I can use this to start my discussion. The question is, if I have these things, how I should describe this distribution of charges? So it's at this point that often we invoke a Boltzmann distribution. And when we invoke a Boltzmann distribution, as you probably remember from Eduardo's talk, we introduce one approximation. I'm assuming that I have point particles, that they obey to these distributions, and they don't see each other. So we miss the interaction between these point particles. And we also are treating them as point particles. So I'm neglecting they have a size. So everything that is in this area here has no size. So these are the typical approximations that we have. And in fact, it's thanks to such things that very often we call these approximations, because we are assuming things. We can start, I mean, this is again a Poisson equation without the solvent. I put the solvent here. We assume this distribution. We can write the equation, put them in this distribution for both co-ions and contra-ions. We make a replacement here for this density. And doing so, we can end up, for instance, in this form of the Poisson-Boltzmann equation. But what usually is also missing is that if you can see the representation, let me go back here. Look that I was using one letter for my electrostatic potential, and then I have another letter when I'm invoking the Boltzmann distribution. Did you notice this difference? One is the electrostatic potential. The other is the average potential. When I'm making these things to be equal here, I have to assume this approximation, that the potential that depends on all the neighborhood is going to be equal to the potential that you have in your electrical field, due to your electrical field. And this is why this specific approximation is called mean field approximation. And it's at this point that we're going to neglect ion-ion correlation. So I'm just going back to the details that Eduardo briefly mentioned to you, and here you have the source of it. So when you do a simulation using the same model, and you solve, I mean, you're solving the same model using Monte Carlo or molecular dynamics, you don't invoke this approximation. You have explicit ion-ion correlation. So that's where, at some point, you can have a breakdown also of the Poisson-Boltzmann approximation. And often what we do is not to work with the linear, non-linear form, but also to do a linearization. So essentially what we are doing, I mean, to write that exponential, and we just make this expansion, and we get rid of these high-order terms. We just keep the small one, and that's why we also have to assume more things. We are assuming that this number is smaller, which is also another approximation. So all these things, in some way, they were present in the Tanford-Kirkwood model. So all these approximations were there. And this is the reason why you could see the difference between the plots when you have the Monte Carlo data, the Tanford-Kirkwood, and eventually the nonlinear version. There you could quantify this for the proteins. We can go on, I mean, just to show you the equations, but you already have seen this equation written by different ways before, so I'm not going to spend the time here. I just would like to make another comment more specific about key parameters that we have here. Because equations, you can easily just take one of the slides that you have seen, either this one or the ones from Eduardo, you can get a good view. But let me just highlight a few points. One is the ionic strength, so the salt concentration effect. This is going to tell you how big is the screening parameter that we are discussing. And this is going to be the ingredient of the so-called Debye or Debye-Hückel screening length parameter. This is the ordinary one, the classical one. This has no dependence of the contra-ions. We also have a modified version of these guys where we include the presence of the contra-ions. This is, you can read a little bit about this in the Beresford-Smith work, where they have introduced it here in the dielectric, in the screening length, the contributions, the screening also from the concentration of any species that can be charged in your system. In this version here, only the electrolytes that are here are going to participate, as you can see here through this eye. But you can have the modified version where you include other charges. There is also something called the Debye-Hückel length. That's a property more related to the solvent. So as you can see, in this equation I have charge, I have the elementary charge, the Boltzmann constant, temperature 4 pi, the dielectric constant of the vacuum, and the dielectric constant of the solvent. So this is a measurement. How is the screening that comes from your solvent? To give you a number, water at room temperature has a Debye-Hückel length of 7.1 angstrom. So this gives you a number. We know that when two molecules or two charges are separated for a distance bigger than 7.1, they're going to be screened. Okay? So that's why it's good to know these numbers. They tell you something about how far you can go from this, in terms of separation distance to see a screening parameter. I think it's somewhere we were discussing, maybe it was with some people, or either in the working group or it was in a coffee break, that when you try to solve the Poisson-Boltzmann, we have to be careful what salt concentration you have, because you need to estimate this guy to know where you can cut your system. If you have your protein somewhere here, you make your box, and you're going to assume that here you have a potential equal to 0. You have to guarantee that this separation distance is larger than the screening that you have. Otherwise, you are going to assume that something is 0, even if it's very much different than 0. So just to try to relate it, things that we have been discussing before. You have also seen this picture, the electrical double layer, so where you have the adsorptions here of the contra-ions. You have a region here where you change the mobility because there's a strong attraction and strong repulsion at the same time. And then you have what we call the bulk of the solution, very far away, where you recover the traditional behavior of the particle. So there is a tendency for particles with opposite charge to aggregate here and particles with the same charge to be far away. Okay, this is something that we have seen. And at this point here that usually we use here as the external layer, we can also approximate and say that we have the zeta potential that Eduardo introduced to you. I think Eduardo also make a comment about the different techniques that you can use to solve. Often in this package that I was mentioning, MEAD, the one from Bashford that I use in that calculations, people use this focus policy. So you start putting your simulation box very big and your protein very small, as you can see here, and then you start giving a zoom until you reach the description that you want for your system. This is a typical thing. And you use in your simulations, you can use the problem, you can use the softwares, not just like MEAD, but you can also use the PBS that I already mentioned. There is a web interface. It's also part of a PyMol. If you are familiar with molecular packets, in PyMol you can add APBS. If you prefer to use online softwares for the same thing, there is a version that's called H++. So they do more or less the same thing. Okay, so the main difference could be the solver that's there, the force field that you are using, how this is going to be implemented, but the general ideas are more or less the same. And these, let's say, softwares or packets or servers, they are dealing with the protein described in atomistic details typically. So you take the structure from the PDB, and then eventually you can make a crude version like the Tanford-Kirkwood model, but you start from the PDB. Just to try to summarize the comparison between the two things, so I can put here the molecular simulation, I mean Monte Carlo, I mean molecular dynamics, and I can make a comparison between Poisson-Boltzmann. So there are pros and cons as always. Just to try to show you a little bit of my opinion, like Poisson-Boltzmann, I already said that's a mean field approximation, and you saw why when I make I make the assumption that the two potentials are equal to each other. In Monte Carlo, on the other hand, you have an exact solution. You take the model and you solve it. That's basically for any Monte Carlo or molecular dynamics. Here is more numerically stable. Here, the nonlinear form can give you trouble. There are versions, like Eduardo is using one, that does not have this problem. But in general, most of the packets, they have problem when you go to the nonlinear version. Here, it's good to work with simpler protein models. Here, you don't have split ions. You describe them as point particles obeying the Boltzmann distribution. We can add the protein concentration as a parameter here because I can define the simulation box, and I can put everything like inside a volume that I don't let particles move away. So I can confine everything inside a box. I can get rid of periodic boundary conditions, so I can define a volume for this space, and if I know the volume and I know the number of particles, I know the concentration. Here, typically, we assume an infinite dilution. It's harder to simulate high salt concentration because you increase too much the number of particles. Here, it might break down when you increase the ionic concentration. So if you have ion-ion correlation, at some point, it's going to break it down. We also have a difference in time. Typically here is more memory consuming, but it's faster. And here you essentially have more time consuming. I think with this kind of a comparison, I can also address questions about what could be the strategy. I think it was you that made me a question about If we're going to study evolution, for instance, what can be a strategy? What can well, if you have lots of proteins to simulate and you have a good computer for memory, perhaps here can be a good approach. If you are going to simulate things and don't have too much and you need a little bit more to play with things like this, eventually you can go to the side, just to try to provide you with practical insights to guide you through all these options that are available. Because if you're a beginner and you read all the options, just the options you could see during the school, maybe you're going to get lost. So how should I start with? There are classical data for this comparison between the two things to show you when you can have problems. So Roland Nets came up with a very nice equation called the electrostatic coupling equation. That's the equation that you can see here in the top. And this equation tells you that this number, if it's bigger than 1, you should have ion-ion correlation effects. In other words, as much as this number is different than 1, at some point you are going to have problems with the mean field approximation, any mean field approximation. So, and also you can have, another way to say is that when you have this number bigger than 1, it means that ion-ion correlations are going to be important. Just to understand a little bit, what we have here is the valence of the contra ions. You have here the Biron length, and you have the charge, the surface charge density of your system. So if you increase too much the charge of your system, you can see that this number is going to increase. But what's more important is the valence of the contra ions, because they go to the power 3. So just change from monovalent to trivalent, I'm multiplying the number by 27. So this is an easy way to see how big this number can be. Just a very brief, a very short estimation, but it can tell you a little bit of the system. And in fact, if you do experiment to make this kind of comparison, I'm taking here a work done by Bouyanson and other guys on the 80s, where they were comparing between 2 plates, the pressure. And you can see the agreement or not between Monte Carlo and Poisson-Boltzmann, or the breakdown of Poisson-Boltzmann depending on the system that you have. The solid lines that we have here, they are Monte Carlo simulation, the dash are Poisson-Boltzmann. And you can see the difference between if you have monovalent or divalent. In the case of the monovalent, they are more or less on the top of each other. So there are differences, but at least they are okay. I mean, it's just the same kind of difference that we observed for the Tanford-Kirkwood model. But if I change, instead of having my system, monovalent contra ions, I just replace them by divalent contra ions, you can see that they start, depending on the charge of the system, we even have a qualitative difference between the two approaches. So these things guides you to know in which regime you can use each technique. It's faster by one side, but you have to be careful with the limitations. This is due to ion-ion correlation. And you can see that you have increased the contra ion. So these are data quite old. And now I'm moving a little bit to more recent developments where we start using these ideas, these historical ideas, to develop models that you can use for constant pH calculation. We have, let's say, classified the methods in 3 classes. We have ones that are more empirical methods, or let's say more statistical-based methods. Maybe they have a little bit of physics, but in general, they are more using information available from the experiments to try to come up with a predictor that can tell you how it's going to be the electrostatic properties, especially pKa's. And one example is ProPKa. That's a typical software that people are being using, and I can put this in this class. Then we have methods that are related to molecular dynamics, and the others that are related with Monte Carlo. Here we have the time-dependent process. I already discussed a few things also in the groups. I'm going to try to review a few points here. And here's more a stochastic approach, as someone else asked me. Okay? So I'll try to go through these things. To try to give you an overview of all the, let's say, better subdivisions of all these methods, we can start with how the things have been developed. I mean, one community was more focused on this kind of approach, more colloidal-like things, where typically it was, the main assumption was to keep the models rigid. So it's a rigid description of your protein. You neglect the dynamics of the system, you neglect internal degrees of freedom, and you assume a rigid description of your protein. On the other hand, there were people developing things more on the lines, like maybe the key word can be Grommak's approach, where you have atomistic description, and everything should be explicit. Water, your protein, and your ions. At the very beginning, if we take this class of models, people were using what I said, constant charge simulation. So typically, you know the pH that like to make your simulation. You use any tool to predict the pKa's, could be even experimental input. You know that the system, that particular histidine should be protonated. You assume that net charge state, you run your calculation. But during all the simulation, you don't change the charge. So the neighborhood effect that I mentioned to you when I was describing pH does not exist. If I have a histidine here and there is an arginine there, of course when I put them together or closer, there should be an effect. But in a constant charge model, the only effect that it can be is like if this is negative, this is positive, they're going to stay closer. So don't let the system change the protonation states. This is what I mean by constant charge simulation. And the majority of the papers that you can see when people are doing molecular dynamics simulations is using constant charge models. Tomorrow, I'm going to show you what happens when you neglect for some system the effect of the pH. The effect of the pH in the sense that the charges can fluctuate as a function of pH. So at the beginning, they start doing that, and in order to correct for it, they start coupling their MED with some kind of titration scheme. One of the landmarks works here is from Batista, Antonio Batista, a guy from Portugal. And he has coupled Grommak's with MED, a Poisson-Boltzmann solver. So using a Poisson-Boltzmann solver, they were able to do titration. And they were able to let the charge fluctuate as a function of pH. I come back to this. So titration was finally introduced and people started doing the constant pH simulations. There were other improvements here to try to better describe this titration scheme. So if you improve the titration scheme, you improve the description of your system. And there are different implementations, of course, making some things slightly different, but I could easily pack it then into these classes. Other people also took these guys and decided to do a kind of simulation where we introduce a kind of dummy particle. It's called lambda particle. And this particle has a kind of some kind of properties like mass, charge, these kind of things. And you introduce this as you were able to move this particle. So you incorporate this in your Hamiltonian. And doing that, you have a class of models that even you can introduce a titrable water. I would like to make it clear that all these models, they are taking a process that's, of course, a quantum process and treating this process in what we call an effective way. So we know that we are not doing the reality. We are trying to describe reality using a simplified model. So we incorporate the effects that we believe they are more relevant to be able to describe what we need. Doesn't matter which style, which flavor of these models you are using, at the end, we are all doing approximations, different ones, but to try to mimic as best as possible nature. But we are not doing any quantum calculations. And by nature, these processes are quantum in their origin. We have a proton that has to move and you have to break down bounds. So in principle, we should use quantum mechanics. But it's already too complicated to deal with these models using this kind of simplified versions. So it will be impossible to do this using quantum mechanics with the resource, at least, that we have nowadays. Okay? But keep in mind that we have an effective description. It doesn't matter which one you are picking up here. They are all effective models. And of course, I showed here things that were under construction, under development here, to try to highlight to you that this game is not over yet. There are developers that are in need of developers in all the directions here. For instance, these models, in principle, they try to be more realistic because you are making your water molecule even titrable. But then you end up into convergence problems. So people are working hard to improve the convergence of this model. So they work more on the algorithm part and the implementation part to try to see if they can come up with something faster that can can in some way help them to solve the model in a reasonable CPU time. I'm going to show you a little bit more data soon. I didn't make too much comments about this, but I think you got the feeling. We can start with a very crude description, the colloidal-like description that I mentioned. We can go to the Tanford-Kirkwood model. You can improve a little bit in introducing atomistic representation and have a Poisson-Boltzmann description, or equivalent, or not equivalent, but next step, Monte Carlo. And also, there is another titration scheme that we introduced a couple of years ago that we simplified a little bit more the things. The description, instead of atomistic, we go to atomistic level, and we got very amazing results when we compare to experimental data. I will describe in more details this model, and also the coupling of this model with molecular dynamics to have what we call it now OPEP6. That's a new force field where we can have titration together for conformational changes altogether. Okay, so I come back to these things. Just to mention a little bit about, to start these constant pH methods, I would like also to show you that if we're working with MED, we can go from explicit solvent methods to implicit, but we can also have hybrid methods. So here I was more describing the two possibilities, like continued description, implicit models, or explicit models, but you can also have hybrid models. The whole idea of this description is like this. You do your molecular dynamics. From time to time, you pass your coordinates and the charge state that you have to a Poisson-Boltzmann solver, for instance. In this case, using MED. Then you do your electrostatic calculations. So you stop your MED, you call the titration, you update your charges back, you don't change the coordinates, and you continue your molecular dynamics simulation. So depending on the position of the titrable groups, now they are going to see each other. So if I have a histidine close to an arginine, they are going to see, and probably they are going to change their protonase state in a different way if they were apart from each other. So look into the environment, how is the distribution of charge for that specific configuration that you are passing here. You are going to update the new charges. So you get new charge that you plug there, and you continue MED. And doing that many, many times, at the end, it's hopefully, you hope that you are going to get something reasonable. So this is the, let's say, a central concept that has been used. Of course, there are assumptions and approximations in this because I'm doing a process that's time independent and just going there, take a snapshot and plugging back. But it's an effective model, so that's the best that can be done, and this has actually started to be done several years ago. You can see that the paper is from '97. The lambda dynamics, as I said, you introduce explicitly a lambda potential. You also introduce a chemical potential where you can see here the introduction of the pH and the pKa0 as we have in the experimental data. So we put a phenomenological description to describe the pH. pH enters into the game here as a chemical function. So we specify pH in our Hamiltonian. I put a number here. And for each titrable groups, I take the experimental behavior and plug here as pKa zeros. So this is the chemical contribution that you have in your Hamiltonian. So this is what goes when you are solving Newton's law. Okay? So that's, of course, I'm not going into all the details. Come on, this is just to flash you with the difference and the key ideas of the methods. So don't have the impression that I'm covering in deep all the subject. It's just really to point you out a few things that are important for these models. But you can see that there is a potential explicitly for this lambda particle. So I'm introducing a new particle in the system. And I have to be careful because I cannot put a proton here with mass 1, otherwise I'm going to have problems to solve my motion equations. So also something that we can discuss. Just to give you an idea about methods, I'm trying to highlight here what I think are the most popular techniques using MED. I already mentioned the one from Antonio Batista. I'm using here one example from Bernard Brooks. You have also these guys here from Germany, and Sereno Domini is now in Finland. So they are doing also another version of lambda dynamics. And Benoit Roy is introducing a new version that also couples MED with MEC in this hybrid method. So these are, let's say, the most popular methods that you can find. There are other, of course, other implementations. We have a review paper that you have available on the Google shared documents that you can take a look in these methods and see how they can be useful. But let me continue just make a few more comments before we close. I mentioned to you about convergency. You can see for 3 proteins here, one of the models from another student from Brooks, Jana Shane, and you can see that she has a titratable water molecule, so she's really trying to work in the all-level description, I mean, when you put all the details, and you have the comparison between the experimental pKa's measured in your simulation and the ones that it calculates. You can see that some points have a very different, results. So there are problems, even if you put all the details. Okay, and you can see here, not just for proteins, but looking to different amino acids. So it seems to be pretty hard to reproduce this glutamic acid over there. You can see the deviations. And these are calculations using all the details that you can put in the model. Okay, just to see how much time it takes for convergence. In her model, it takes about 10 nanoseconds for you to reach convergency. So you spend 10 nanoseconds just to get the proper charge of your system. And smaller proteins, of course. In the case of Benoit Roy, it's even more critical, the results. Here he has a dipeptide. So we are talking about 2 amino acids together. And in this case, using his method, it takes about 40 nanoseconds to have a convergence. So it was looking in the literature and observing these kind of things that we decided to create a new model. The history of this model, of course, is not specific for this purpose. We have been working a little bit with this. But in short, we have in mind that we need a model that could let us do the calculation on the bioinformatics side. If you remember, I mentioned on my second talk that the key difference between computational chemistry, computational physics, and bioinformatics is probably that we need to put this on the large scale, right? And on the large scale, it means that I should be able to reproduce or repeat the calculations for different experimental conditions or different mutations. So we have to keep in mind that I need this. And if I have to wait 40 nanoseconds per simulation just to equilibrate to get to convergence, it's going to be impossible to use. It's going to be prohibitive. So with these things in mind, trying to describe things like pH, ionic strength, and mutation effect, also try is not the best word. Aiming to getting the free energy of the system, we need to simplify. And I'm going to describe this model in details tomorrow. Okay, I think my co-organizer granted me 2 more minutes, but I think I can make this point to stop, and I can resume from this point tomorrow before you sleep here in the classroom. Okay, it's going to be difficult, I guess, tomorrow morning because probably you're going to be even more exhausted. But I hope you can save some energy so I can talk to you for about 1 hour before you have your group presentations. And I think this is a good point, as I said, to stop, but it's also a good point to remind you some things that people were asking me just before the class. The group presentation is something simple, but you should emphasize what you have learned in the school, not what you know before you came into the school. What we are after is to try to see what you have learned during these next days. Don't tell me about the dancing class that you were taking during the previous days. Don't tell me about your samba or beer experience. We need to know what you have learned in the class, in the lecture halls, and the work group sections, more related to the topic that you made a choice. Okay? You can make questions if you want. I don't need to rush. Or we can leave it for tomorrow or whatever, the way that you prefer. Okay, so have your studying hours and work hard for a nice group of presentations that's going to be recorded tomorrow. So you're going to be on YouTube. Thank you.